Fine. So we'll be starting with the chapter on rheology and viscosity. So in this chapter, we are going to study about what is viscosity, what is rheology, what are the different types of rheological properties, the different flow properties of fluids, and deformation of solids. How do you measure them? All right. So maybe over a course of 3 lectures, we'll be completing this topic. All right. This is again, there's some concepts in this topic which are really important. So please pay attention to that and try and understand it in a way कि तुम लोग को बाद में ज़्यादा time इस पे spend ना करना पड़े. All right. So let me know if you can see the screen. So try and understand the terms properly. Okay. Can you see the screen?
Yes.
Okay, fine. So in this part, we'll study about the basic definitions and what Newtonian flow is. All right. So rheology is a term, again, it's a Greek term, which is coined by these two scientists, Eugene Bingham and Crawford. All right. These are the two scientists who coined this term and who studied the science of rheology. So what rheology means, logy or logos in any term means the study or the science behind it. All right. And rheo means flow. So the flow of fluids or the deformation of solids, how are these fluids going to behave under different sort of pressures, okay, different type of pressure, shear rates, time dependent properties, also temperature dependent properties. So all of these things are studied under the umbrella of rheology. So tumhara viscosity, thixotropy, pseudoplastic, plastic flow, all of this comes under the science of rheology. And rheology, all these physical aspects of science, they're not, it's a very generalized topic. So you have rheology being studied in apna pharmacy, pharmaceutical sciences mein aata hai. It comes in civil engineering also. Can anyone have a vague idea how will civil engineers use the science of rheology? I want this to be an interactive class. It shouldn't be a one-way thing. And it's okay if you all are, I don't mind if you all give wrong answers at this stage. But I want you all to participate.
Viscosity of the construction materials required.
Yes, the flow, matlab kitne like during building, constructing roads, laying roads, uska concrete and the tar and all, how is it going to behave under pressure of those rollers and all of that? How is it going to spread? So even those sciences are used, like this science is used in these areas, fine. And in our cases, though, it has a vast application. You see the way the toothpaste is coming out of the tube, right? How well is it going to come out? If it is very viscous, very hard, it won't come out even if you are applying pressure. Agar viscosity bahut kam hai, okay, if it's more fluidic, it's just going to run out from the tube. Fine. You don't want those things to happen. That is why you need to study the science of rheology. Even it becomes important in suspensions, emulsions, and all of these liquid preparations and semi-solid preparations. Fine. And when you characterize the behavior, when you study it quantitatively, that is called as rheometry. Fine. So Do you see this animation here? एक जगह force perpendicular लग रहा है surface को. This is the surface horizontal and force is coming from the top. And एक बाजू tangential लग रहा है. So in rheology, when I'm saying जब हम pressure apply करते हैं, force apply करते हैं, so here I'm talking not about this perpendicular force, but I'm talking about this tangential force which is being applied. Okay, so it becomes so what you need to understand here, the rheology में जो हम force apply कर रहे हैं, all of that is tangential to the surface. Okay, so this is called as your shear stress, जो tangential लगता है surface को, and उसके वजह से जो deformation होता है उसको shear strain बोलते हैं. Okay, and normal stress के वजह से जो होता है that is compression. So rheology में your semi-solids and all of that में we are studying basically this tangential force. Can you all tell me ये perpendicular force कौन से dosage form में important होता है?
Tablets.
Very good. Tablets, even capsules, while filling or tapping of the capsule. All right. So these are the different two major types of forces. So now when you're applying this tangential flow force to a surface, ये square से एक slant square था पहले, तो square से एक slant position में आ जाता है, it becomes like a rhombus, correct? So this is the position what it's coming into. It initially was a cube, but when you're applying this tangential force, now I will call it as stress. Okay, when you're applying shear stress to it, it's coming in a rhombus form. All right, so let us try and understand the different terminologies by this representation here. So the difference of velocity between the two planes of liquid. Now when you're applying shear stress here, these layers, ऊपर के जो layers है वो faster flow होंगे या move होंगे, वो faster move होंगे compared to the lower layers, correct? So the difference in their velocities, okay, which is separated by a distance of r or dr, infinitesimal distance, that is called as shear rate. Okay, velocity ka difference between two layers which is separated by some distance, that is called as shear rate. And speed, okay, so uska units will be second inverse, time inverse. And shear stress is the force per unit area. Force is nothing but, okay, pressure is nothing but force per unit area. So the force per unit area required to bring a flow, that is called as shear stress. तुम्हारा normal pressure का definition is just force per unit area, but the force per unit area जिससे flow तुम produce करते हो, that is called as shear stress, and the units are same as pressure, that's pascals. And ये जो deformation हो रहा है, मतलब जो cube से जो rhomboid बन रहा है, that deformation or the change in shape or size, that is called as shear strain, and that is measured in radians. So that is a shear strain is a geometric property. I hope you all are writing it as in when I'm saying things. Yeah. So this is a geometric property. So समझा सबको what is shear rate, shear stress and strain? Hello.
Yes. Yes.
Okay, good. So now let us discuss Newtonian viscosity. Because ये जो भी flow होगा, wouldn't it be also dependent on कितना viscous है तुम्हारा material? Correct? It will also depend on how viscous your material is. अगर material ज़्यादा viscous है, then how will the flow be? How will the flow be?
Flow.
Flow. And तुम्हें stress कितना apply करना पड़ेगा, कम की ज़्यादा?
ज़्यादा.
ज़्यादा.
Obviously ज्यादा apply कर. If it's something is difficult to flow, viscosity क्या? The resistance to flow. Okay, So अगर कोई चीज में ज्यादा रेजिस्टेंस है फ्लो करने को, तो तुम्हें ज्यादा फोर्स अप्लाई करना पड़ेगा for it to flow, right? And now I won't use the word force, I'll use the word shear stress, because we are talking about the flow of fluids. Fine. ज्यादा स्ट्रेस अप्लाई करना पड़ेगा तभी वो फ्लो होगा. Fine. So this is your shear rate, okay? dV by dr is your shear rate, and this is your shear stress. So shear stress is directly proportional to the shear rate. जितना ज्यादा तुम shear स्ट्रेस अप्लाई करोगे उतना फास्ट चीजें फ्लो होगी, करेक्ट? सो दे हैव डायरेक्ट, इट्स डायरेक्टली प्रोपोर्शनल, राइट? फाइन, इट्स डायरेक्टली प्रोपोर्शनल. एंड देन वो प्रोपोर्शनैलिटी को एक कांस्टेंट दे दिया ईटा, which is nothing but your viscosity. All right. So when I take eta on this side, so it becomes F by G, matlab shear stress upon shear rate, correct? So can I say viscosity is directly proportional to the shear stress? Can I say that? Jitna zyada viscosity, utna zyada shear stress required, right?
Yes.
Yeah. And opposite about the shear rate, जितना ज्यादा viscosity उतना कम उसका rate of flow होगा, right? So that is what your viscosity is, and eta is nothing but your coefficient of viscosity or absolute viscosity of your material. In general, whenever you use the term viscosity, it's representing eta, okay? And fluids following this law. Now, they're not all the fluids which behave like this. This is one anomaly which is being explored in the science of rheology. Fine. Ideal case में यही होना चाहिए कि जितना ज्यादा तुम फ्लो अप्लाई करो, स्ट्रेस अप्लाई करोगे, उतना ज्यादा विस्कोसिटी होगा वो सब्सटेंस का. Now, there are some substances which do not follow this law. So Newton studied this system and he categorized it based on this equation. The fluids which are following this law, okay, of direct proportionality, कि मैं जितना ज़्यादा stress apply करूँगा, उतना तेज वो flow होगा. Those fluids are called as Newtonian fluids. And obviously the ones which are not following this are called as non-Newtonian fluids. Fine. So what he did is he plotted a curve of shear rate, okay, that is your G versus shear stress, okay, shear rate versus shear stress. And because the fluids which showed a direct proportionality, okay, a straight line passing from the origin, okay, those fluids are considered as Newtonian fluids. Fine. So this is your standard curve. Fine. A plot which is passing from zero, a linear line, okay, this represents that shear rate is directly proportional to shear stress. जितना ज्यादा तुम stress apply करोगे, उतना तेज या उतना easily will it flow. So this is what Newtonian fluid is. Is it understood, everyone?
Yes, ma'am. Yes, ma'am.
I believe you all understand that. If you all have any doubts, you all can pause me then and there. Fine. And right now, I think you're a handful only, so it can become easier for us to interact. Fine. We won't end today's class with any question mark. Fine. So let me know if there are any doubts. And now this is a scientific or technical definition of viscosity. But basically viscosity is nothing but resistance to flow. So the shearing, and agar ye hum equation dekhe, I don't know why am I not able to use the pen here. Just a minute. I'm not able to use the pen here, sorry. Okay. So shear force required to produce a velocity of 1 centimeter. Okay, ये इक्वेशन पकड़ो तुम, eta equals to F by G, shear stress upon shear rate. Fine. So the shearing force required to produce a velocity of 1 centimeter per second between two parallel planes of liquid, jiska distance or area is 1 centimeter square and separated by a distance of 1 centimeter. So viscosity is that force which is required to produce this velocity. Fine. And these are the different SI units, units of viscosity. Just have a look at it. You all need to know the conversions here. Fine. So uska SI unit to Pascal seconds hai, viscosity ka. Just a minute. Okay, the viscosity, the units here are Pascal seconds. And in CGS system, when you convert it, it becomes 10 poise. All right. And 1 centipoise, when you're measuring in centipoise, it is 0.01. All right, that is the thing. And the opposite of viscosity is fluidity. Okay, opposite of viscosity is fluidity. Fluidity is nothing but the ease with which a fluid will flow. And uska phi hai symbol 1 upon eta. Clear, everyone? Hello.
Yes, ma'am.
Okay. Now let us understand kinematic viscosity. So kinematic viscosity is the real-time viscosity, because I hope you all understand that there's one more factor which comes in viscosity is the density of the material. Abhi tum same material lo, okay, and kind of and this is a derived property, okay. Kinematic viscosity is derived from your viscosity. So if you're making a solution, water का viscosity अगर तुम study करोगे, plain water का, that is your absolute viscosity, or the viscosity वो eta वाला, okay, that is this. But अभी तुम water as a solution का viscosity study करोगे. For example, if you dissolve some polymer, sodium CMC, suppose तुमने water में dissolve किया, और वो system का if you are studying the viscosity, then that becomes kinematic viscosity. All right. Obviously तुमने water में अगर कुछ डाला तो viscosity water का तो अलग ही हो जाएगा. And now you won't be studying viscosity of water. You will instead be studying viscosity of that new system. Agree?
Yes.
Hello. Yeah. Fine. So that study is kinematic viscosity. अभी तुमने उसमें सोडियम CMC suppose dissolve किया, but एक में तुमने 5 mg डिसॉल्व किया, एक में 10 mg, एक में 20, एक में 40, एक में 50. Wouldn't their viscosities also differ? Let me tell you, sodium CMC is a viscosity builder. Okay, so जितना ज्यादा तुम concentrate करते जाओगे, उसका viscosity of the entire system will change accordingly. It will increase accordingly, ideally, right? So kinematic viscosity में we are studying the viscosity with respect to the density of the overall system. Fine. So your kinematic viscosity, okay, is the absolute viscosity divided by the density of a liquid at a specific temperature. At a specific temperature, because temperature के साथ साथ भी तुम्हारा viscosity change होगा. Imagine if a system is at room temp 2 to 8 degrees Celsius पे, मतलब फ्रिज रेफ्रिजरेटेड है, एक रूम टेम्परेचर पे है, एंड एक से 40 या 50 डिग्रीज पे है. से योर शुगर सिरप ऑफ सेम कॉन्सेंट्रेशन का शुगर सिरप you have at these three different temperatures. Tell me, how would the viscosity be? Hello.
At
Hello.
higher temperatures, the viscosity will be low.
Low. बाद में give me the order which will be the high ज्यादा सबसे ज्यादा viscosity कौन से टेम्परेचर पे रहेगा?
At
The
lower
lowest
temperature.
one.
Then I give you three conditions: refrigerated, room temperature and heated condition. तो viscosity ज्यादा किस में रहेगा?
Refrigerated.
Then
Room temperature.
Room temperature.
and then heated. Heated वाले का सबसे कम रहेगा. So when you want to study the effect of density, हमें ये temperature constant रखना पड़ेगा. In science, whenever you want to study the effect of one thing over the other, हमें दूसरी सारी चीजें constant रखनी. अगर हम दो चीज एक साथ change करेंगे, then we don't know कि effect किसके वजह से, right? So in this case, we keep temperature constant. So kinematic viscosity of the systems are measured at room temperature, ambient temperature. Fine. You're just changing the density. So that is what the difference between absolute and kinematic viscosity is. Okay. So what is it telling you? This relates the viscous force of the inertial force by relating the Newtonian viscosity of a fluid to its density at a constant temperature. इसका भी unit same ही है. Pascal seconds and Stokes or centistokes. So that is why हमें HPMC के ना अलग अलग grades होते हैं. HPMC 15,000, 5,000 and all of that. Fine. So that is nothing but के उसका कितना viscosity will it create. For example, HPMC 50 करके आता है. It has a viscosity of 50 CPS, centipoise. If it is 15,000, HPMC 15,000, वो 15,000 CPS पे हो. All right, so that is what it is. Yeah, you can see in the animation here. It's the same material of different concentrations. So see, ये कितना easily flow हो गया, ये थोड़ा fast हुआ, ये उससे slow हुआ, and these two are the not flowing only. It's taking so much time. So this is how it will affect. Fine. So एक चीज हो गई तुम्हारा डेंसिटी कॉन्सेंट्रेशन, दूसरा चीज हो गया तुम्हारा टेम्परेचर. एंड एज आई टोल्ड यू, एज टेम्परेचर विल इंक्रीज, विस्कोसिटी कम होगा एंड इनडायरेक्टली फ्लूइडिटी बढ़ेगी. यू टेक एग्जांपल ऑफ दिस कैंडल ओनली. जहां पे ये विक जल रहा है, द ऊपर वाला पार्ट ऑफ दिस कैंडल, दैट वैक्स इज रनिंग. ओके, दैट वैक्स इज मेल्टिंग because उसका viscosity कम हो रहा है. When you're providing thermal energy to this wax, which is at room temperature, it's solid. Okay, solid, we'll say super viscous. Okay, when you're providing thermal energy, तुम उसका by providing thermal energy, molecules के बीच का kinetic energy बढ़ेगा and it will space out more. That's how it will become more दूर and viscosity कम होगा and it will start flowing. Whereas नीचे का part जहाँ पे उतना temperature exposed नहीं है, it still remains solid. Right? So this is a classic example of how the temperature dependence of viscosity. Fine. तो उसको study करने के लिए this is one equation derived, which is like eta equals to AE raised to EV by RT. So where A is a constant which depends on the molecular weight of the liquid and all. It's a constant dependent on the system. EV is the activation energy. I'm telling you now, the thermal energy required to create a flow or to initiate a flow. Okay, so activation energy which required to initiate a flow. So that is what it is. R is gas constant and T is temperature and Kelvin. So this is how temperature and energy is being related with your viscosity. And ये एक statement note down कर दो that the activation energy for flow is 1/3 of the energy of vaporization. मतलब the point जहां से तुम्हारा system vaporize होने लगेगा, उसका 1/3 will be your activation energy to initiate flow. Solid से flow होना चालू होगा, liquid बनेगा, and liquid से it will become gas, correct? So that's why it's 1/3 of the energy of vaporization. Is it clear, everyone?
Yes.
Pakka?
Yes.
Okay, good. So this was about Newtonian fluids. So Newtonian fluids mein what we studied, what is the absolute viscosity? Then we understood uska derived property, that is kinematic viscosity. Kinematic viscosity में हमने कौन सा parameter change किया and कौन सा constant रखा? Hello, question पूछ रही हूँ मैं. Kinematic viscosity में what were we changing and what did we keep constant?
Viscosity was changed.
Viscosity तो you are studying, but with respect to what?
Density.
Correct. Density you are changing, and what are you keeping constant?
Temperature.
Temperature. Temperature. Fine. And kinematic viscosity and iska units will be same. And what about this thing? Temperature dependence mein what are we changing? We are studying viscosity with respect to change in temperature.
Density.
टेम्परेचर डिपेंडेंस में डेंसिटी कहाँ से आया? टेम्परेचर डिपेंडेंस मतलब वी आर चेंजिंग टेम्परेचर. समझा ना सबको? हेलो, अंडरस्टूड?
Yes, ma'am.
Yes, ma'am.
थैंक यू. एक यस आने के लिए कितना रुकना पड़ता है? So this was about non-Newtonian fluids, Newtonian fluids. Now I told you कि in nature you have things which don't follow this Newtonian system. माने कि हमें क्या लगता है, shear stress increase किया तो flow बढ़ना चाहिए ideally, और वो भी proportionally. But कभी कभार क्या होता है, तुम shear stress increase करो ना तो in fact flow कम हो जाता है. That means it becomes more viscous. Or else at times what happens कि shear stress तुम increase करो and proportional increase होने के जगह it will increase exponentially. मतलब थोड़ा तुमने shear stress बढ़ा दिया तो viscosity कुछ ज्यादा ही कम हो गया, मतलब it became more fluid. And at times what happens कि you are applying shear stress, nothing is happening, but after a point it will start flowing very easily and very fast. So these are different things, right? These are anomalies. These aren't the regular things what you expect. It's not a linear trend. And those systems are classified as non-Newtonian systems. Fine? And there are different types of non-Newtonian fluids. In your syllabus, there are 3 major things which we are going to study: plastic flow, pseudoplastic flow, and dilatant flow. But actually, there are more flows which are being discovered and found out. जो ये 3 में नहीं बैठते, थोड़ा अलग ही trend दिखाता है. So they are classified in a different way. Okay? So ये usually कौन से type के systems ये चीज exhibit करते हैं? Dispersed systems. Okay? Such as your suspensions and emulsions, or fluids that contain macromolecules, which are having high molecular weight. They usually do not obey your Newton's law, and that's why they are classified as non-Newtonian systems. And non-Newtonian fluids may exhibit different rheological behavior depending on the shear rate, shear stress, and also temperature. Temperature dependent property भी होती है, time dependent भी होती है. मतलब for certain time it will certain time तुमने shear apply किया, it will flow. बाद में if you remove that stress and keep it for some time, it will again become solid. Then it will again start to flow. All right. Example, your toothpaste only. तुमने toothpaste को, you applied shear stress, it's coming out of the tube. So वो fluidic हो रहा है. But does it continue to flow over your toothbrush? No, it remains there. तो वो gel to salt to gel बन रहा है. So that comes under thixotropy and rheopexy and all of that, which we'll study in the forthcoming lectures. Fine. And yeah, so there are categorizations of these non-Newtonian fluids, which are called as pseudoplastic, dilatant, Bingham. And it's not a rigid classification. Fine. You cannot say कि ये चीज compulsorily यही flow करेगा. It will depend on the environment. It will depend on the entire composition. You cannot say suspensions are pseudoplastic. No, there are some suspensions which can be pseudo, some which can be dilated. Okay. And as I told, time-dependent Rheo properties are rheopexy and thixotropy. Right? So yeah. So when you plot this shear stress versus shear rate, और उसका एक्सिस कभी कभार उल्टा भी हो सकता है, shear stress इधर आ सकता है, shear rate इधर आ सकता है, तो ये पूरा opposite हो जाएगा. So such a plot is called a rheogram. Okay, these are called as rheograms. And now tell me, which fluid is this straight line passing through zero?
Newtonian.
This is Newtonian flow. Now I told you there are some fluids जो after shear stress apply करे कुछ नहीं हो रहा है, but after a certain point it will have some flow. That is called as your plastic flow or Bingham flow. So let us first try and understand this plastic flow and Bingham flow. Fine. This diagram is taken from your Martin book. I would recommend you all to study this chapter from Martin. Fine. So here you see either axis change किया है. Instead of shear stress on y, either shear stress x axis पे है. Shear stress versus rate. So तुमने apply किया stress only after a certain point it is flowing, and this flow is also, you can say it's proportional only, more or less. So this point, okay, this point of shear stress जहां से तुम्हारा flow initiate होगा, okay, this point, that point is called as yield value. So yield value is an important parameter when you're studying plastic flow. And plastic flow was vastly studied by the scientist Bingham. So the systems which obey plastic flow, unko Bingham bodies bhi bola jata hai. So Bingham bodies exhibit which flow?
Plastic flow.
Plastic flow. Okay. And plastic flow ko Bingham flow bhi bola jata hai. And the systems which follow that are called as Bingham bodies. Fine. So the plastic flow is associated with the presence of flocculated particles in concentrated suspensions. This is one important point. More or less, usually concentrated systems will exhibit this flow, concentrated suspensions, and that also the ones which are flocculated. I hope you all have an idea of flocculated, deflocculated. We'll be studying about that property in depth when we do coarse dispersion and suspensions. Okay? So concentrated suspensions जो flocculated होते हैं, they exhibit your plastic flow usually. Okay. Consequently, the yield value is an indication of the force of flocculation. Matlab, the more flocculated the suspension is, the higher will be the yield value. Now tell me, I don't know why is the pen not working here. Let me try and use this. Okay. Tell me, abhi there is system A, jiska flow ऐसे है. Fine. This is system A. This is system B. And this is system C. Now tell me which system is A, B, C में से, which system is more flocculated and is having more force of flocculation?
B.
What?
B.
Why B?
Because the yield value is higher.
अरे बट इधर C भी तो बनाया है मैंने. C is starting from this point. B is starting. God, it's so windy today. C is starting from this point. B is starting from this point, and A is starting from this point. इधर क्या बोल रहे हैं? Higher yield value, more flocculated. तो किसका yield value higher है?
C, ma'am.
C.
Correct. C का yield value higher है. So can I say C has more force of flocculation? C has a greater degree of flocculation. Can I say that?
Yes.
Yes.
तो C सबसे ज्यादा है. Second number पे क्या आएगा?
B.
Second number पे B आएगा. And then you have A. Fine. So this is what it is. So by studying rheology, you will also understand the properties of a particular system. For example, suspensions here, even emulsions. Emulsions भी flocculated, deflocculated होते हैं. हाँ? So by default, इधर suspensions के साथ emulsions भी आ जाएगा. I'm sorry for the handwriting. Fine. So this is the equation here. अभी the slope of this curve, ये curve का जो slope आ रहा है, that slope is called mobility. Okay. And it is the reciprocal of plastic viscosity. जैसे viscosity and fluidity होता है, वैसे plastic viscosity and mobility होता है. So mobility is the ease with which your plastic body or your Bingham bodies will flow. So slope जितना ज्यादा है, जितना steep है, it will be more easy. It will be more mobile. Those Bingham bodies will be more mobile, more easy to flow. Okay. And here the F, small f, is the yield value or the intercept on the shear stress axis here. Okay. And F and G to pata hai. F is what? Shear stress or shear rate?
Shear stress.
And G is shear rate. Fine. Yeah. So as shown in the following
Ma'am,
example.
can you repeat the graph again?
तो ग्राफ में मैंने
Can
यही
you
बोला
repeat the graph again?
या ग्राफ में मैंने यही बोला है कि जो स्लोप मिलता है तुम्हें, दैट स्लोप इज मोबिलिटी. जैसे नॉर्मल केस यू हैव विस्कोसिटी एंड उसका ऑपोजिट इज फ्लूइडिटी. फॉर बिंघम बॉडीज यू हैव प्लास्टिक विस्कोसिटी एंड यू हैव मोबिलिटी. सो मोबिलिटी इज द ईज विथ विच योर बिंघम बॉडीज विल फ्लो. दैट्स इट. गॉट इट खुशी?
Yes.
Okay. So once the yield value has been exceeded, any further increase brings about a proportional increase in rate. हमने न्यूटोनियन सिस्टम्स में पढ़ा है कि न्यूटोनियन सिस्टम इज डायरेक्टली प्रोपोर्शनल फ्लो दिखाएगा. बट इन केस ऑफ योर plastic bodies also, after it crosses this yield value, it will show a proportional increase. After it crosses the yield value, it will show a proportional increase. So can I say that Bingham bodies behave like Newtonian systems after its yield point? Can I say that?
Yes.
Yes. Fine. Only after the yield point, it will more or less behave like a Newtonian system. Fine. And how much proportional it is, matlab slope will tell us about the mobility. So in effect, a plastic system resembles Newtonian system at a shear stress above the yield value. Fine. So ye thoda extrapolate kiya. So this region from ye shear stress se leke, where did the pen go? ये पॉइंट से लेके ये पॉइंट तक, ओके, फ्रॉम दिस shear stress, okay, इतने shear stress के region में, इतने shear stress के region में, it is going to behave like a Newtonian system. Can I say that in this area? समझा सबको?
Yes.
Good. Good. You know, whenever you all see any graph or see any plot, you all should try and understand what is it trying to tell you. A graph, a plot will always speak to you a lot. Okay. So by this graph, you get to know what is the yield value. You get to know how mobile the system is. You will get to know the range in which कौन से shear stress पे that system is going to behave like Newtonian system. So, you know, these studies will actually help you designing the systems. Suppose if you have a material which is having a plastic flow. Okay, suppose you have a material which is having a plastic flow, and only on a certain point you want it to flow, or at a certain point you don't want it to flow. तो तुम उसको वैसा shear stress provide नहीं करोगे. ओके, या फिर यू वांट अ सिस्टम कि जिसका यील्ड वैल्यू बहुत ज्यादा हो ताकि इट रिमेन्स इंटैक्ट. कितना भी तुम स्ट्रेस अप्लाई कर दो, इट इज नॉट गोइंग टू फ्लो, इट विल रिमेन इंटैक्ट. सो यू विल एड सम एडिटिव्स जो इसका यील्ड वैल्यू शिफ्ट कर देगा. सो दैट इज हाउ दिस इज गोइंग टू प्ले, और दिस इज गोइंग टू हेल्प यू इन फॉर्मुलेशन साइंसेस, इन फार्मास्यूटिकल साइंसेस. समझा सबको एप्लीकेशन पार्ट?
Yes.
Good. So we are done with Newtonian systems. We are done with plastic systems. Now let us move on to pseudoplastic system. Pseudo matlab false plastic system. So if you look at the graph, अपना plastic system का graph कैसा था? Plastic system का graph ऐसे था, correct? इधर से चालू होता था, एक yield value से चालू होता था. Pseudoplastic graph भी ग्राफ नहीं, रियोग्राम. Pseudoplastic का रियोग्राम भी ऐसे ही दिखता है प्लास्टिक सिस्टम जैसे, बट इट डजंट हैव अ यील्ड वैल्यू. इट विल स्टार्ट फ्रॉम द ओरिजिन इटसेल्फ. ओके, so let us understand. Okay, it will start from the origin itself. That is why it's pseudoplastic. प्लास्टिक का यील्ड वैल्यू होता है, pseudoplastic का यील्ड वैल्यू नहीं होता. Fine. So let us look into this. So now this is usually exhibited by your macromolecules or your long chain polymers and all of that, pseudoplastic. So long chain polymers ko jab, you know, you put it in a dispersant. This is your dispersed phase, and जिस vehicle में तुम उसको डालोगे वो dispersion media हो जाए. So when you disperse it in a media, वो ऐसे ही randomly arranged होगा, entangled होगा. Okay. So when it is entangled, no, तभी इसके बीच में you will have your water molecules in between. Okay, let me mark it in green. You will have your water molecules in between, entrapped. Entrapped नहीं, फंस गया होता है. Agree? Correct? Okay.
Yes.
When it's randomly dispersed, long chain polymers बीच में lot of तुम्हारा dispersion media वो entangle हो जाता है. But when you apply shear stress, okay, in form of say stirring, when you're stirring also, that is a form of shear stress. So when you're stirring, what is happening is that these are, okay, when you're applying shear stress, it is aligning itself. Okay, and कैसे align कर रहा है? It is aligning in the direction of flow. तुम ऐसे shear stress apply कर रहे हो, so it's aligning in the direction of flow. And when you're aligning it in the direction of flow, जो भी ये entrapped होता है, जो बीच बीच में अटका होता है, वो सारा free हो जाता है. Okay, it becomes free. So in a way, सिस्टम में ज्यादा डिस्पर्शन मीडिया आ गया, जो पहले फंसा हुआ था, नाउ इट इज फ्री. ओके, इट इज फ्री. तो overall the apparent viscosity of the system will decrease. Agree or not? Because ज्यादा मीडिया रिलीज हो गया है, ज्यादा मीडिया फ्री फॉर्म में हो गया है. So there's more free movement, there's more fluidity in the system. So it has, the viscosity of the system has apparently decreased. Correct? So when the viscosity of the system is apparently going to decrease, the flow of the system is going to increase, and that flow is your pseudoplastic flow. So, okay, the solvent associated with the molecules, ye phase pe jo solvent associated tha, will be released, resulting in an effective lowering of the concentration also, and not the size of the dispersed molecule, but basically there'll be a decrease in the apparent viscosity. So that is why after a point, as you apply shear, you are releasing more and more vehicle or dispersed molecules. You're bringing it more and more into the system. You are decreasing the viscosity more and more. And when you decrease the viscosity, the flow is naturally going to increase in that system. So that is why these systems are called as pseudoplastic flow. ऐसा नहीं है कि after a point of stress flow increase होगा. Starting से ही वो increase होता जाएगा. That is why you have उसका graph which is passing from the origin. So पहले धीरे धीरे बढ़ेगा and then exponentially उसका flow बढ़ेगा. Is it understood? And these are some examples. Understood, everyone?
Yes.
Okay. Can I go ahead now?
Yes.
Everybody, Pragnya, Divya, Madhura.
Yes, ma'am.
Yes,
Okay,
ma'am.
very good. So this was about pseudoplastic flow. Acha, iska graph I showed you all, it's like this, right? Because tabhi shear stress niche tha. So don't get confused. When you have shear stress here, okay? When you have shear stress here and rate here, tabhi tumhara pseudoplastic ulta ho jayega. So in exam, the reason why I'm putting both the graphs here, in exam, be careful के axis पे कौन से जगह पे क्या है. इधर तुम्हारा stress होगा तो this जो अभी इधर pseudoplastic system, dilatant system दिखा रहा है, that will become your pseudoplastic system. So exam में आँख खुली रख के you all answer the MCQs. All right. Check what are the axes. And can anyone tell me why pseudoplastic system is called as shear thinning system based on my explanation?
As
Because at some point the viscosity is decreases.
हाँ, तो shear के वजह से वो पतला होता जा रहा है, viscosity कम होती जा रही है. That's why shear thinning system. And why is it called pseudoplastic? That also you all understood. Look, this is okay. Got it? Now there are some, yeah. Now there are some systems. I told you now there are more systems. ये तीन तो ये चार actually तुम्हारे syllabus में majorly है, but there are more systems. So there's one more which I want to bring to your notice because वो US Pharmacopoeia में दिया है. This graph is actually taken from USP, US Pharmacopoeia. Fine, and that's why I want to bring to your attention about the Herschel-Bulkley plot or the Herschel-Bulkley type of rheogram system flow. It is nothing but a combination of your plastic system and pseudoplastic system. Because like plastic systems, even Herschel-Bulkley plot will have a yield value. Okay, even it will have a yield point or a yield value. Whereas, like a pseudoplastic system, look at its behavior. Even after that yield point, only after that yield point, it will behave like a pseudoplastic system. So can I say Herschel-Berkeley plot is rheogram, or Herschel-Berkeley fluids are a combination, or yeah, they're somewhere in between your plastic system and pseudoplastic system. Got it? And these, yeah, this iska example are your biological fluids. Usually, biological fluids like your synovial fluids, even your blood in that case. So your biopharmaceutical biofluids usually behave like this. So जैसे जैसे ना नए flows people keep on discovering. So ये scientists के नाम पे नाम दिया जाता है. Fine. So which type of fluids exhibit Herschel-Berkeley type of flow?
Biological.
Biological fluids. Synovial fluid पता ना क्या होता है? Synovial fluid.
Present between the bones.
Yeah, present between two articulating joints, like your ball and socket joint on your shoulders, your knees, okay, elbows.
Ma'am,
Huh.
can you explain this one again, the Herschel-Berkeley?
Herschel-Berkeley में मैंने यही बोला है कि it's if you see, it's like a combination of your plastic system and your shear thinning system. Like your plastic system, उसका भी प्लास्टिक सिस्टम का भी यील्ड पॉइंट होता है, Herschel-Berkeley का भी यील्ड पॉइंट होता है. मतलब only after a certain stress, only after that threshold will it start to flow. And once it starts to flow, how will it look or how will it behave? It will behave like a pseudoplastic system. Okay, look at the curve. It's parallel to your pseudoplastic system. Plastic में कैसा? After the yield point, it will behave like a Newtonian system. Herschel-Berkeley में after a yield point, it will behave like a pseudoplastic system. Got it, Madhura?
Yes, ma'am. Thank you.
Ma'am, but the Herschel-Berkeley system, the graph was passes through origin, right?
नहीं, Herschel-Berkeley इधर से पास हो रहा है, yield point से.
Okay.
I'm telling you ना, it's a combination of pseudoplastic में origin से पास हो रहा है. Got it, Khushi?
Okay.
Yeah. So it's a combination. So there are two. ये diagram में, tell me which are the two flows which have to have some yield point, which will only flow after a certain shear stress. Which are the two flows? Hello.
Plastic and Herschel-Berkeley.
Berkeley plot. Now let us look at, अभी हमने pseudoplastic समझ लिया, shear thinning, कि shear apply करने पे viscosity कम हो रहा है. I told you there are also some systems in nature जो shear या stress apply करने पे उसका viscosity बढ़ जाएगा. Okay, the more you apply shear, it will become hard. घर पे भी तुम्हारा example है. Your आटा को तुम जितना गूंदोगे, it will become hard eventually, right? So those are your dilatant systems. मतलब they are dilating, they are becoming more viscous, and that is why they are called as shear thickening system. Systems जो thicken होगा because of shear, that is called as shear thickening system. So as तुम्हारा shearing stress बढ़ेगा, the rate is going to decrease. मतलब you will need more rate for it to flow. So yeah, dilatant systems are exhibited, मतलब this behavior is exhibited by concentrated suspensions which are deflocculated. Flocculated systems कौन सा flow दिखाएगा?
Plastic.
Very good, plastic flow. And pseudoplastic कौन से materials दिखाएंगे?
Long chain molecules.
Long chain polymers, your hydrocolloids and all of that. Fine. So dilatant behavior is exhibited generally by your concentrated suspension, 50% or more concentrated hona chahiye. Non-aggregating deflocculated particles. Fine. So what happens is that you see this diagram here. Initially, closed packed system hai. Now these are your particles in pink, and black mein you have your dispersion media. Closely packed particles, minimum void volume hai. Okay, minimum void hai, spaces hai. And जो भी vehicle है आजू बाजू में, it is sufficient. Okay, it is sufficient for the wetting and for the movement of the particles, and they are relatively low consistency. But when you increase, when you apply shear stress, what happens is these particles tend to move away from each other. Even in pseudoplastic, they tend to move away from each other. But in that case, वो जो भी entangled solvent था उसको free कर रहा है. यहाँ पे क्या हो रहा है, कुछ भी entangled नहीं था, but उतने ही volume में imagine more spreading out of the particles. So they are dilating in a way, and now there is increase in the void volume, जिसके वजह से there is insufficient vehicle now. जो vehicle जो इतने में enough था for it to move and flow, abhi because it's expanding, because it's dilating, now this is insufficient. Because it's insufficient, now it's going to exhibit higher viscosity. Okay, so that example is cornstarch and water. Atta, basically, your ceramic and starch dispersions and all of that. Starch का तुम लोग ने अगर tablet बनाया रहेगा college में, when you're making that starch as a disintegrant, right? Mixing it with water, तुम ज्यादा mix करते जाओगे ना, वो eventually it's going to thicken. If you notice किया है ये कभी? किया है कि नहीं ये experiment? Tablets का?
No.
Not yet. You all will eventually do it. Okay, so तभी notice when you all have make some atta. जितना ज्यादा तुम उसको stress apply करते जाओगे उतना वो hard होता जाएगा. Fluidity कम होती जाएगी. So this is how dilatant systems are working. They dilate, and that is why they decrease the apparent, मतलब they decrease the viscosity. So ये कब problem होगा? If you imagine, if you have a big tank, जिसमें you are making some dispersion like this, जिसका nature is a dilatant flow का nature है वो system का, okay, and तुम stirrer से उसको घुमाए जा रहे हो, but instead of it behaving same, घुमाए जा रहे हो at constant speed, say 50 rpm पे तुम घुमाए जा रहे हो, but instead of it behaving same way, वो thicken होते जा रहा है. So तुम्हारा stirrer को ज्यादा effort लेना पड़ेगा. Okay, in fact ज्यादा thicken हो जाएगा तो तुम्हारे stirrer पे ज्यादा load होगा. It can spoil the machine. Agree or not?
Yes, ma'am.
Agree?
Yes, ma'am.
So yeah, that is what, when such systems increase in volume when the shear, and hence the term dilated. Okay, this behavior suggests appropriate precaution to be taken during processing of dilated material, as they may solidify under the shearing condition, and thereby they might overload or damage your equipment because of this constant stirring. Okay, but one thing what happens is when you remove this stress, a dilatant system returns to its original state. That is one thing. When you remove stress, जब stirring बंद कर दोगे, it can eventually, it might, it depends. Again, it depends on the nature. It may remain like that, solidified, or it may again come back. So this becomes time dependent, and that we will study in detail when we are studying thixotropy and rheopex in the third lecture. Got it, everyone?
Yes, ma'am.
So that is why तुम्हारी rheology, again you need to study, because तुम्हारे processing techniques and all of that will become very critical हर एक स्टेज पे कि वो मटेरियल कैसा है तो मुझे कैसा प्रोसेसिंग टेक्निक यूज करना पड़ेगा. सो इन दैट केस मैं बहुत कम, इंस्टेड ऑफ 50 आरपीएम में 10 आरपीएम पे चलाऊंगी. ऑलराइट, कम टाइम के लिए चलाऊंगी. कि इतने time में it will not become solidified, it will be good for my machine also. Fine, got it?
Yes, ma'am.
Yes.
So this is, and that is why it's called as shear thickening system. So how many systems did we study? Newtonian, plastic, shear thinning, shear thickening, and one additional Herschel bulk layer. So now let us look at the applications in detail. Selection of processing equipments. मैंने अभी बोला. What kind of this is a mixer, right? What kind of mixer is this? Pharmaceutical engineering पढ़ा है तुम लोगों ने?
Yes.
तो कौन सा type of mixer or crystallizer is this?
Ribbon blender.
Very good. This is a ribbon blender. And this entire is like a Silverson mixer, if I'm not wrong. But this is a ribbon blender. Okay. So imagine इसमें तुम तुम्हारा dilatant system डाल रहे हो. Eventually वो इतना solidified होगा कि तुम्हारा machine ये blender move ही नहीं होगा. And that will cause lot of overloading on the machine. Heat up हो जाएगा. It will be broken down. It will might cause breakdown of the instrument. So that is why study of rheology can help us in selection of processing equipment, right? Then mixing and flow of materials, all right, which is the same thing. How well will it mix and all. Packaging into containers. What kind of pump is this? Come on, my lectures won't be restricted to only the topic. I want you all to interconnect things. ये कौन सा pump है? Any guess? Any guess? Reciprocating pump. आगे पीछे जो move होता है, that's a reciprocating pump, right? Yes or no?
Yes, ma'am.
So it's important to know your fluid because this also in a way applies shear. It looks like a compression thing, but it overall applies some shearing stress to your material, right? And if it is pseudoplastic, तो eventually वो बहुत ज़्यादा flow होगा. Then at a time instead 10 ml अगर fill होना होगा वो 15 ml fill हो जाएगा because it's more fluidic. वरना अगर dilatant होगा तो instead of 10 ml वो eventually कम होते जाएगा fill volume. So that is why for packaging also it becomes important, and you will, that is why standardize your parameters. Dispensing of the formulation, you don't want your formulations to be very viscous or very runny. Okay, even when you're dispensing suspensions from the bottle. Physical stability. Okay, patient acceptability. If your ointment is too runny, that will be a problem. If not spreadable, then that will be a problem. Bioavailability. When you are having say syrups and all, okay, you want it to have वैसा viscosity कि you are taking it out of the bottle and the spoon तभी easily flow होगा. But when you're consuming it, it should adhere to your throat, right? Your expectorants. It should adhere to your throat so that the molecules or the API can be absorbed in that region, in that mucus membrane. Fine. So tumhare, that is going to affect your bioavailability also. If it doesn't adhere, okay, if it is very less viscous, more fluid, it is going to go down your throat. It's not going to retain in your throat. So drug ka bioavailability in the location hoga, nahi hoga. Effect, therapeutic effect milega, nahi milega. So see, this becomes important at so many levels, from the processing, manufacturing, filling to dispensing and its therapeutic effect. So understood everyone the applications of rheology?
Yes.
Yes, ma'am.
मजा आया पढ़ के? No. No or yes?
Yes.
Yes, ma'am.
All right. So do you all have any questions? Any questions?
Ma'am, I have one.
Yeah, tell me, Madhura.
In in kinematic viscosity, we know that we keep temperature constant and density changing, but is the viscosity also changing?
Obviously. See, this is kinematic viscosity ka formula. Kinematic viscosity is your absolute viscosity upon density. Okay? Matlab, less, yeah, it's inversely proportional. Your kinematic viscosity. Density, not concentration. Fine?
Ma'am, isn't
Now,
absolute viscosity always constant?
yeah, absolute viscosity will be constant. Absolute viscosity is an attribute to your system. मैंने वही तो बोला, पानी का viscosity same रहेगा, बट पानी में अगर तुमने सोडियम CMC डाला तो चेंज होगा, पानी में अगर तुमने शुगर डाला तो उसका viscosity अलग होगा. That is kinematic.
So, ma'am, in kinematic viscosity, we in place of absolute viscosity, we take the absolute viscosity of the solution, right?
No. You take absolute viscosity of your media.
Like of water?
Yeah. That's what I'm saying. Kinematic viscosity is your derived property. So जब तुम solution की बात करते हो, जब तुम system की बात करते हो, तब तुम kinematic viscosity बोलो. Ideally.
Okay, ma'am.
Got it?
Yes, ma'am.
Okay. So can we solve a few MCQs, or are there any more doubts? Okay, I'm assuming no doubts. So first question. Who quantitatively studied the flow properties of liquid? Huh?
A.
Okay. Any other answer?
C.
C is the correct answer. Newton quantitatively studied the flow properties of liquid. That's why he could give the equations. Bingham and Crawford studied the phenomena of rheology. All right. Quantitative study of flow properties are by Newton. Next. Let me put all the questions on screen. Question 2.
B.
Plastic.
Plastic body, Bingham bodies. Dilated को कौन सी system बोलते हैं?
shear thickening,
Pseudoplastic को?
shear thinning,
Very good. Which of these do not follow non-Newtonian flow? Do not follow. Okay, first tell me.
NaCl injection.
Very good. NaCl injection do not follow non-Newtonian flow. They are Newtonian. They are only Newtonian. ठीक है? Low molecular solutions and all, they follow Newtonian's law. Okay? ये सब जो high molecular होता है ना, suspensions हो गया, water in oil या oil in water, तुम्हारा emulsions हो गया, ointments हो गए, they all are non-Newtonian. Fine? Your low molecular normal solutions are Newtonian. The force per unit area which causes flow is called
Pressure.
Shear.
which causes flow.
Shear stress.
Correct. Shear stress. Force per unit area is pressure. Force per unit area which causes flow is shear stress. Be careful, okay? Clear everyone? Viscosity क्या होता है?
Resistance to flow.
Fluidity
Reciprocal of viscosity.
or, in other words, ease of flow. Okay? Hello?
Yes, ma'am.
Shear rate,
Difference of velocity between two planes of liquid.
correct, which is separated by some distance. Herschel-Berkeley system exhibit which of these flows? कौन सा?
A.
A, plastic, pseudoplastic. And okay, plastic, pseudoplastic. Fine. Very good. Let me put all the questions. Yeah. Question 6. Dash system exhibit increase in viscosity with increase in shear.
E.
Huh?
Dilatant.
Dilatant. Increase in viscosity with increase in shear. Pseudoplastic का क्या होगा?
Decrease in viscosity.
With increase in shear. Plastic का?
Yield value.
Flow on after a certain shear stress, after a yield point. ठीक है? Herschel-Berkeley system will show increase in viscosity after a yield point. Which of these deals with biorheological systems?
A.
A.
Herschel-Berkeley. Plastic system का क्या है?
Concentrated flocculated
Flocculated.
suspension.
Flocculated. Correct. Dilatant का?
Deflocculated.
Deflocculated. D for dilatant, D for deflocculated. And pseudoplastics, तुम्हारे macromolecules, your long chain polymers. P for polymers, P for pseudoplastic. Easy?
Yes.
Which of,
Yes, ma'am.
this is how you try and remember some things, okay? Which of these flows at all the given shear stress? हर shear stress पे it will flow.
Pseudoplastic.
Pseudoplastic.
Very good. Herschel-Berkeley nahi because it requires yield point. Even plastic requires yield point. Dilatant system, तुम shear stress जैसे बढ़ाते जाओगे उसका viscosity बढ़ता जाएगा and eventually it will stop flowing at a point. So not dilatant also. So pseudoplastic is the correct. Which is a time dependent rheological property? हाँ, कौन सा? Thixotropy also, and even rheopexy. Both of these are time dependent properties. Fine. That we'll study in the third lecture. Temperature is directly proportional to viscosity. True or false?
False.
As temperature increases, viscosity
Decreases.
all right. Very good, girls. Yeah, all of you are girls only. Okay, so with this, we come to an end of the first part where we studied the different terminologies and different classifications, right? In the next lecture, we shall study about the instruments used to measure viscosity and rheological properties. In the third lecture, we'll study rheopexy and thixotropy. All right?
Yes.
Okay. So yeah. See you all, everyone. Okay, bye-bye. We'll meet maybe next Sunday or next month. Let's see. Fine?
Thank you.
Yeah, bye-bye.
Thank you, ma'am.
Thank you.